Welcome. Have you ever really thought about the journey the power in your outlets takes? Today, we're going to trace the incredible path of solar energy, starting from the fiery heart of a star 150 million kilometers away, all the way to the sockets in our homes. We'll get into the science and the engineering that makes it all possible. So let's dive in. All right, here's our game plan. We're going to start at the source, of course, the sun itself. Then we'll follow the sunlight on its long trip to Earth. After that, we'll check out the two main ways we put that energy to work. First, by capturing its heat, and second, by turning it directly into electricity. And finally, we'll see how all these pieces fit together to build the solar systems that are powering our world.
Okay, first things first, we have to start with our star. Every single watt of solar power, every bit of warmth we feel from the sun, it all begins right here.
Just take a look at this. It really puts the scale of what we're talking about into perspective, doesn't it? The sun's diameter is a massive 1.39 million kilometers, and it's about 150 million kilometers away from us. I mean, it's just mind-boggling. But even from that incredible distance, its energy is strong enough to power all life on Earth. And you know, that huge distance has a really interesting side effect for engineers. It means that by the time the sun's rays get to us, they're traveling in almost perfectly parallel lines. And that little fact, as we'll see, is absolutely crucial for designing efficient solar collectors.
So, what is the sun really? Well, at its core, it's just a gigantic, non-stop nuclear fusion reactor. Deep inside, the pressure and temperature are so intense that hydrogen atoms are literally squeezed together until they fuse and become helium. This whole process unleashes a tremendous amount of energy that radiates out into space. And it's this constant, powerful reaction that's the ultimate source for pretty much all the energy we have here on our planet.
So that energy shoots across the vacuum of space in the form of radiation. But its journey isn't over just because it reaches our planet. What happens next is a really big deal. Let's find out.
So the sun is pumping out this insane amount of energy in all directions. The big question for us down here on the ground is, how much of that power actually makes it to our doorstep? To answer that, engineers need a baseline, a starting point, and that's what we call the solar constant. You can think of it as the raw, unfiltered power of the sun measured right at the very top of our atmosphere before anything gets in the way. The standard value NASA uses is 1367 watts for every single square meter that's facing the sun. That is a lot of energy.
But of course, that's not what we feel on the ground. Our atmosphere acts like this giant protective filter. Some of that incoming energy gets absorbed by gases like ozone and water vapor, which heats up the atmosphere. And the rest gets scattered around by air molecules, which, fun fact, is the reason our sky is blue and why we have that soft indirect light on a cloudy day.
Now, for engineers, especially the ones designing technologies that concentrate sunlight, it is absolutely critical to measure only the direct sunlight, that straight shot from the sun. That's where this nifty device, the pure heliometer, comes in. It's a specialized instrument designed to block out all that scattered, diffuse light and measure only the direct beam of radiation. Okay, so now we know how the energy gets here and how we measure it. Let's look at the first major way we actually harness it, by capturing its heat, or what we call its thermal energy. When you boil it all down, there are really two main approaches to this. On one hand, you have flat plate collectors. These are the simple workhorses. They can absorb both direct sunlight and that scattered, diffuse light. They operate at lower temperatures, and they're pretty straightforward in their design. On the other hand, you have focusing collectors. These use mirrors or lenses to concentrate sunlight onto a tiny area, which lets them get way hotter. But, as you can imagine, they're a lot more complex. Here's a perfect look at a basic flat plate collector. It's really just a dark, insulated box. That's it. It's designed to absorb as much solar radiation as it can to heat up a fluid, usually water or air, that's flowing through it. Some designs, like the one you see here, add some simple mirrors just to give it a little performance boost. Now, let's jump over to the focusing collectors. This is a compound parabolic concentrator. Check it out. It uses two specially curved mirrors to gather sunlight from a pretty wide area and focus it all down onto a much smaller receiver. This lets it get much hotter, much faster. And here's another really cool design, the mirror strip collector. Instead of one big, bulky mirror, this uses a whole series of long, flat mirror strips. Each one is angled just right to reflect sunlight onto a single focal line, which is usually a pipe with some fluid in it. This setup is great because the receiver can stay fixed while the smaller mirrors move to track the sun. Oh, and this one is just brilliant. This is a Fresnel lens. You might have seen something like this in an old lighthouse. Instead of using a single, thick, heavy, curved lens, it's made of all these concentric rings.
Each ring has a slightly different angle, which allows this big, flat, lightweight lens to concentrate all those parallel light rays down to a single, intensely hot focal point. Super clever. Okay, so we've seen mirrors and lenses, but what if there was a way to collect and store solar heat on a massive scale without any of that? What if you could turn an entire pond into a giant thermal battery?
Well, you can. It's called a solar pond, and here's how it works. Sunlight shines through the water and heats up the dark bottom. Now, normally, that hot water would rise, cool off at the surface, and the heat would escape. But in a solar pond, you create this super salty, really dense layer of water at the bottom. That salty layer is just too heavy to rise, so it traps the heat down there. You can get the water at the bottom up to 90 degrees Celsius, all while the surface stays cool to the touch. It's pretty amazing.
So, we've covered capturing the sun's heat, but what about turning its light directly into electricity? For that, we need to zoom way, way down into the world of quantum physics and talk about something called the photovoltaic effect.
This right here, this is the heart of all solar electricity. It all happens inside a solar cell, which is usually made from silicon. When a particle of light, called a photon, hits the cell, its energy gets absorbed by the silicon, and that kicks off this remarkable little chain of events.
Let's break it down. First, a photon from the sun comes in and smacks the silicon atom, knocking an electron loose. This creates what's called an electron-hole pair. You've got your free negative electron and the positive hole it left behind. But that's just chaos. The real genius is in step 3. The solar cell has a built-in electric field that acts like a traffic cop, forcing all those free electrons to move in the same direction. And what is an organized flow of electrons? That's an electric current. So that whole photovoltaic effect is happening at an almost microscopic level inside just one little cell. But to power a house, let alone a city, you're going to need to scale that up a lot. So let's see how we go from a fragile little cell to a powerful and robust system.
You see, a single solar cell is incredibly thin and fragile. You couldn't just stick that on your roof. To make it useful in the real world, it has to be protected. And we do that by packaging a bunch of cells together into a tough, weatherproof unit called a module. They're basically sandwiched between a sheet of glass on the front and a durable backing sheet, and then the whole thing is sealed inside a sturdy frame.
So let's just clarify the terms here because you hear them used all the time. The cell is the fundamental unit, the little guy doing all the work. A module, which most of us just call a panel, is a group of those cells all wired together and protected in a frame. And an array is when you connect a bunch of modules together to create a large-scale power system like what you see on a solar farm. It's really just a simple, scalable building block approach.
And there you have it. From nuclear fusion in the sun's core, to light traveling across the vastness of space, to being captured as heat in a salty pond or as electricity in a tiny silicon cell, it's amazing when you think about it. We've figured out how to turn a distant star into the power that lights up our homes and charges our phones. So as we keep pushing forward, the real question is, what's the next frontier in our quest to harness the sun's incredible, endless energy?